fundamental symmetries, checking of fundamental symmetries. Institute of Space Science is involved in Alice experimental cell, so there's strong interaction in high energy collisions. And the University of Ioannina, also represented by Professor Cosmas, is also involved in muon decays and other related topics. So we can think about to have an overlap of event on this subject in the future. So we open this session, morning session, with Caterina presentation from Frascati. Sorry, Caterina, if you want first to say something, you are co-organizer, so it is not mandatory.
Well, it is mandatory because I want to thank you because you were pushing for organizing this. So I think I have to thank you very much because that's actually the first workshop I'm organizing in Romania, which it's very, very nice, and I'm very happy to be back here after so many years I'm in Italy. And as Sabine was saying, actually the idea is that we set up the platform for future workshops which should grow in time and get it. What are they doing?
Privacy matters.
Wow, that's bravo, excellent. You found it without even telling me where it is.
Very good.
Cool. Do I have a...
Pointer, please.
Mulțumesc frumos.
Să drag.
So
Okay.
we explain what is a strangeness odyssey.
A Strangeness Odyssey, right. So I have the pleasure to kick off this workshop, and what I wanted to show you, it's a presentation, an overall presentation of what I was practically doing for last 20 years. And actually it's an odyssey because it took much longer than we originally thought. And I think that many of you are with me in this because usually things take much longer than one initially thinks, unless one is totally happy or totally bored of what is being done. And what we are doing is to study the strangeness physics, namely the low energy kaon nuclei and nucleon interactions, which is related with the strong interaction, the quantum chromodynamics. And it's also, of course, in this context related to the symmetries which Sabine was mentioning before. What symmetries in this case? Well, it's chiral symmetries, which is of big importance in the universe because, as we may know, the mass of the universe, it's not really given by the Higgs boson and Higgs mechanism, but much more by the chiral symmetry breaking. Before starting, however, let me dedicate this presentation to our professor, the one who was for long, long years key figure for all of us who were working in Frascati in the group of strangeness physics, Professor Carlo Guaraldo, who left us about 1 month ago, and that for us it's absolutely a very big loss. And I dedicate this to him because he was not only a great scientist, but was humanly a person who was absolutely unique. I can tell many stories about him, very also many funny stories. So I dedicate this talk to him. That's the place where we are doing our experiments, those which I'm going to show you the results of today. And that's one of the very few electron-positron colliders in the world, actually the only one practically working in the world, in Europe today. It's called Daphne. It's an electron-positron collider working for more than 20 years. By the way, I want to say here that the electron-positron colliders were born in Frascati since the very first one, ADA, was built there as an exercise by Bruno Tušek and a team of young people in the early 60s. By end of 60s, just the very first collider was starting to be built based on this research. And it was an odyssey. That's why I called it an odyssey, because somehow, like Ulysses going back home, which took much longer than he originally planned, that's what happened to us. To work on this machine, namely the Daphne Collider, and do our experiments, it took much longer since we started these experiments actually we started to think about them more than 25 years ago. And it took so much because we discovered, as usually an experimentalist discover, that there are effects there which you did not consider when you started to plan the experiments. The collaboration which I have the pleasure to be the spokesperson of, it's Siddhartha 2 collaboration, and it includes, it's not big. With respect to today's standard, it's pretty small. We are 40 persons, more or less. But as you see, it's a very vivid collaboration, which includes people from all these countries, not only from Europe, but also outside Europe, specifically from Japan, because they are also doing strangeness physics, and we are strongly collaborating with them. What we are doing actually is we are using the kaons particles which are produced at the Daphne Collider. So kaons are mesons which contain a strange quark, and they are interesting because you can study the strangeness by studying the kaons. And we shoot them into a target which contains atoms, which, if the kaons are very low energy, they are captured in atomic orbits, forming kaonic atoms. So, which are specific class of exotic atoms. Exotic atoms, as you may know, means an atom where the electron is replaced by any other particle negatively charged, which lives long enough to form the atom. And the kaonic atoms are a very specific case. The kaons are trapped into the orbit. They form a very highly excited state, of course, based to the fact that the kaon is 1,000 times heavier than the electrons. So it starts from a very highly excited level, and then it cascades down up to, hopefully, to the fundamental level. Not all the kaons make it through because some of them are absorbed from higher levels, but what we are interested in is actually the transitions to the fundamental level. Why that? Because on the fundamental level, the kaon is close enough to the nucleus to feel not only the QED, so the electromagnetic interaction which rules, of course, the physics of any sort of atom, including a kaonic atom, but in this position, so close to the nucleus, the wave function of the kaon overlaps with the one of the nucleus. That means that the kaon feels the strong interaction, the QCD, so strong interaction between the kaon and the nucleus, and the strong interaction, you can actually measure it by the fact that the atomic level, it's shifted with respect to the electromagnetic, pure electromagnetic calculated value. So you measure something else, and the difference between what you measure and what you calculate, it's purely QCD, so strong interaction. Also, the kaon is absorbed by the nucleus, which also is due to the strong interaction, meaning lifetime, very short lifetime, which means very broad level. So if you are able to measure these two quantities, the width and the shift on the fundamental level, you are able to extract information about the strong interaction, basically at threshold. When you go at threshold, you are at QCD in a highly non-perturbative regime, which is somehow the most interesting regime, because there is where you do not know yet the fundamental theory. So you don't have perturbative methods, you only have potential models, chiral perturbation theory, lattice calculations. So that's the very interesting regime which needs this type of information. And it has been a long journey in which we were not the only actors. So we were doing experiments, and I'm saying we because we are competitors but also friends. So the Japanese colleagues are part of our collaboration, and we are part of their collaboration at J-Park in Japan. So we are doing this type of experiments in these two pillars in the world, meaning in Frascati and in Japan. And it took a long time, you see, more than 20 years, to do experiments. This is the article which actually contains all the details of our study. And yeah, we had a lot of troubles. Again, that's related with the Odyssey. We had a lot of troubles to do this because experiments, because it was much harder than we originally thought, since we discovered that we are overwhelmed with backgrounds. So when we were trying to do experiments, we want to measure radiation. So I forgot to mention that what we do here, it's how we extract this information. We measure the decays, kaonic atom decays, so the radiation emitted in these transitions in kaonic atoms, which 4 kaonic atoms are not like normal ones, like light or something like this, but we go to the X-ray regime. And that's what we measure, and when you measure X-rays in an electromagnetic machine, you are overwhelmed by background. So we had to develop a lot of instruments to fight the background. And this type of studies, the kaonic atoms and the related kaon nuclei interactions, are related theoretic-wise with a lot of very interesting physics. By definition, the nuclear physics and QCD at very low energy, which I already mentioned. But it's also relevant for astrophysics in the equation of states of neutron star, which today is very well and much debated, especially in the context of the strangeness, composition or not of a neutron star. It has also implication. We ourselves published a paper some years ago with the possibility that dark matter is within the standard model and not some other particles, meaning deeply bound kaonic nuclei states. If you want to ask me, I won't mention it more today. And also fundamental physics, and also new physics, because beyond the transitions to the fundamental level, you can stay high in transitions where there is pure QED, and you can study similarly with other like muonic atoms, you can study QED itself. That's, yeah, the neutron star, where the equation of state is still very much open, because that's the key point, whether strangeness play a role, which also give rise to the hyperon puzzle today. And where we do the experiments to this electron-positron collider in Frascati, which is called Daphne, which I showed you before, which, as any other accelerator in the world, it's not only accelerator, but actually it's a series of accelerators, starting with a LINAC. Then the LINAC linear accelerator develops into a booster, into a compact accelerator, which prepares electrons and positrons particles to be injected in the main collider. And the energies of the beams are such optimized that, meaning half of GV, that when they collide, they form the phi particle, the phi meson. The phi meson lives extremely shortly, and it immediately decays into kaons, half of the time in K plus K minus, and that's where we get our K minus. That's a layout of the machine, which it's a very complicated machine. The overall length is about 100 meters, and it's complicated because what you get, it's a lot of troubles to run. When you run with electron and positron beam, it's complicated because you have a lot of synchrotron radiation, which you need to resupply. So it's not an easy machine to. That's how it looks like in reality. And yeah, so that's the mechanism, the electron-positron collisions at energy of the phi. With a cross-section, it produces the phi about 1,000 per second, which decays K plus K minus, which is a very lucky process for us, because being back-to-back particles, you can use this topology to get rid of the background if you are able to trigger on coincidences of kaons, which actually we are doing, and my colleagues will tell something more about this. Okay, so this machine has been used for more than 20 years, both for neutral kaons, which I'm not going to speak about. Neutral kaons were used by Chloe collaboration to study CP violation and rear decays. We are using that for exotic atoms and kaon nuclei interaction. And that's what we are doing. So we cross electrons and positrons, form phi, K minus go into a target, and it produces X-rays, which are measured by, of course, then you need to have a detector able to do the X-ray measurement with possibly a very good energy resolution. And because that's what you'd like to have, the energy measurement, that's what you are aiming, the position. And we started actually one of the first professional experiment. We have done one before which was quite a challenge, but then in 2009 we moved to the first measurement which gave quite an important result in the measurement of conic hydrogen. And conic hydrogen, it's a masterpiece, and it's a fully important piece of information because it gives you the interaction between the kaon and a fundamental nucleon like the proton. So that's what you want to have, kaon proton and kaon neutron to start with. And we had a target filled with hydrogen. Hydrogen, it looks simple. One is tempted to say, go take a bottle, plastic bottle, and I have a target, which in principle is true. But there are some points here. The bottle needs to withstand 20 Kelvin and overpressure because you want to have high density but still gas. So it's a highly cryogenic target, and to stand this temperature and overpressure, meaning about 40 times the normal pressure, you'd like to have very thick walls to stand. But very thick walls, it's counterproductive because then the X-rays don't go through. So it's a complicated process. Even the building of a target which is filled with hydrogen, not to speak about the detectors. And the detectors was itself an odyssey because we were the first group in the world which used and produced by ourselves this type of detector, silicon drift detector, not for position measurement, which is well known and experienced by many years. We use them for spectroscopy, and that's something unusual. So energy measurement and not position measurement. And that's the first bench of detectors we produced in Germany, PM Sensor, and they work very nicely. And the scientific goal is that once you have, that's what you measure, shift and width of the fundamental transitions in hydrogen and deuterium. And that's what theoreticians get, the isospin-dependent scattering length through not a very easy procedure, which is yet very much debated. So that's the theory part, and that's the experimental part. And we work together with a series of theoreticians. It would be nice to extend the collaboration if there is anyone interested. And that's what we measured for hydrogen. When you look, it's not like wow, because the signal was very hard to extract. It's still very hard. It's still the most precise measurement in the world. And it's still a cornerstone for all theories which deal with strangeness. That's the pure kaonic hydrogen spectrum with the whole series of transitions, K-complex, on the fundamental level. And this has been used by many theories to constrain the threshold behavior of the scattering, imaginary and real part of the scattering amplitude. And that was very nice, and that's what this, it's a series of theories developed across the world using various methods. That's the kaon-proton interaction, and that's above threshold coming scattering, and that's below threshold, which means kaons eventually embedded in nuclear matter like the neutron star. So in neutron star you should be deep here, and you see that models are totally diverging. Not to speak about the interaction with the neutron. The interaction with neutron, it's a mess. You see, missing an experimental point, it's diverging totally, which means that's what you have to do next, interaction with neutron. But unfortunately, you can't form kaon-neutron complex. You have to extract it from interaction with deuteron. So you have to measure the kaonic deuterium. And that's what we have done in our, Florin, you are speaking about this. So this is mostly going, I'm only advertising it. Florin is going to speak about this, how we succeeded, and what's the technology which allowed us to extract the kaon-deuterium interaction. So that's our part of our group, and you see part of my colleagues here. It's not all the collaboration with the apparatus, which is very complex, and it took a lot of time He will be here in the afternoon. You may see Simone here. Florin, it's here. Florin is our technical coordinator of the collaboration, and Luca here. So we will have presentations from all three of them. I'm going to jump over all these technicalities because this is going to be addressed. You are addressing this, Florin? So this is going to be addressed by Florin. So what we were doing to achieve the goal with the experiment, tell me what you say and what you don't. You say this?
Yeah.
Okay. Okay, so let me just tell you one thing, that when we are actually, what we were doing before measuring the deuterium, because deuterium is a very hard measurement. You are blind till the very end of the measurement because the yield of transition is extremely low. So you don't know you are doing it totally blind. So before going blind, we measure transitions in neon. You see for high levels, 9 to 8, 6 to 5, which have a yield 100 times higher than the deuterium. So we wanted to see something before going blind. And that's what we measured, which was a test measurement initially. But we discovered that the test measurement, it's extremely successful. So successful that we are now preparing to measure something which is a total puzzle in the particle physics, the Coulomb mass. The Coulomb mass, it's a curious issue, which if it would have happened today, since there are 6 sigma differences here, everybody would have jumped dark matter, extra dimensions, like it's normal. 3 sigma effects now, nobody, it's, yeah, but since it happened in the 80s and 90s, there are 2 Coulomb measurements, 6 sigma far away. So, and this is a pending puzzle in the PDG. And we discovered that we can measure the mass with the conic atoms, with conic neon. Unfortunately, this is only the statistical error because the systematic is 10 times higher and it overtakes that, meaning we need to make a calibration measurement which is much, much better, which we are now developing. And then we were measuring the deuterium. And I only want to advertise that we succeeded finally. That's very preliminary, and it's the work of a PhD student, Francesco Sgaramella, who has really put all of himself to extract. It's not very impressive as a spectrum, but these are the transitions of interest, and that's only part of the statistics. And it looks like we are able, after 40 years of recognition of the importance of this measurement, we are finally pinning it down. And that's how it looks like in comparison with theories. You see there are theories, predictions in the shift and width spread all over. That's our very preliminary point. Don't take it too serious because it might still move. But that's extremely exciting. And we are now moving towards all the statistics, and we are also, right now, this is our last week of data taking. And we are very excited to finish the data taking with another important measurement, another puzzle, the fact that the probability of this transition we can also measure. And what theories are previewing are orders of magnitude differences between the alpha transition here and here and here. So there are 2 orders of magnitude differences between the theories. So we also want to go and try to have a glimpse. We won't be able to measure the pattern, but to have a glimpse into this. And that's very exciting. So that's what we are doing. Ivica, who will come this afternoon from Zagreb University, will also talk about a measurement we are performing in parallel with germanium detectors, pinning down the conic lead, but I leave him to speak about this beautiful measurement. And so that's what he will speak about. And we were also pioneering for the first time, again in the world, the use of another type of crystals, cadmium zinc telluride detectors, in a collider. We put them in the collider. We wanted to see if they survived due to the radiation hardness. They survived. Not only they survived, but we succeeded to measure intermediate mass conic aluminum, which we are now extracting for an article. And with this, I'm approaching the end, telling you that that's where we are. And you will hear some more these days about details of how we got here, and also some, I make publicity also to Luca, because one of the presentations we will do, it's strongly related to its double beta neutrinoless decay, but we were not able to pin down the theory. We don't have theoretical connection. We know it's there, but we don't know which one is. So Luca will speak about this, and I hope it will stimulate discussions. Because for the future, we want to go, we got so nice and that we got so much confident of ourselves that we want to pin down to make a series of measurements across the periodic table. Not that measurements do not exist, they do, but we believe that they are wrong. Potentially they are all wrong, because whenever we were redoing a measurement from the past means 80s, 70s, 80s, whenever we redone one of these measurements, shift and width, we discovered that the measurement was wrong. So we have a hint that there might be all wrong. We also have a hint why: calibration of the detectors, non-linearities in electronics. So we proposed a new initiative, which is called Excalibur, which plans to go through selected measurement across the periodic table. And we have also proposed how to start, so the kickoff of this, which is the Cowan mass I already mentioned. So one cannot stay like this, with a Cowan mass which has two different values. By the way, the Cowan mass problem is the biggest systematic error for LHCb in the B to C, so the B boson, the B meson going to D transitions and decay channels. So that's something we want to do, namely with the Cowan neon, to decrease the systematic error, to put it at the same level of statistics, and pin down the measurement of the Cowan mass finally. So that's what our problem now, the systematics. And for this we also have an idea how to do. Florin has actually proposed a very nice system, a movable target arm inserted with X-rays, a tube which is shining through, which is able to cover all the spectrum and give us a very, very high precision calibration at 0.2 electron volt. The other measurement we plan to do is low Z, so this has been required by theoreticians to move to many body systems, lithium, beryllium, and boron, and this has energy which are a bit higher. So since the energies are higher than our effective energy of present detectors, we developed detectors in silicium which are thicker, 1 millimeter instead of ½ millimeter, which again, for the first time in the world, we produced them, this time in Italy, in Trento at FBK. And this was, for whomever it's intended by detectors knows that 1 millimeter silicon, it's a total mess. It's very hard to do them, but we succeeded to do that. And yeah, we are planning to do this measurement in the coming years. I'll jump over this. That's the nuclear part, but yeah. So, and I'm concluding that the strangeness fundamental physics as we are studying, it's really important and relevant. It's relevant in many sectors, from particle physics, particle structures through the Cowan mass, up to understanding breakout of the symmetries. Which symmetry? Chiral symmetry in particular, which gives the mass to the visible part of the mass in the universe. And it's also connected potentially to cold, dense matter, as in the stars, which can be neutron stars or quark stars and strangelets. And with this, I end up with, since I started with the Odyssey, I end up with a sentence from Homer, the Odyssey: immortals are never alien to one another. Okay, so thank you very much.
Thank you very much, Katarina, for your nice presentation on how to build a world with chaos.
Yeah.
And this is very exciting. So please, if you have comments or questions. Please.
Yeah, these chaotic atoms are really exciting. I mean, they look like kind of hydrogen type of atoms. For leptonic atoms, so to say, ordinary atoms and ionic atoms and so, we know very well the fine structure and and hyperfine structure. How about kaonic atoms? So I mean, where do these corrections start, and where is the only S state which is feeling the strong interaction? I bet it is only S state, the
Yeah.
lowest S state, but otherwise it should be, I mean, governed by electromagnetic
Yes.
interactions, and you have fine structure and hyperfine
Yes.
structure.
Yes, absolutely. And that's an issue. I don't know, Simone, if you will address it somehow, because Simone is an expert in atomic physics calculations. And yeah, that's indeed a problem. So in principle, the strong interaction, it's visible only on the 1s state, at least in light atoms. In heavy atoms, it extends a bit farther away. And even for helium, it's a matter of discussion whether it reaches the 2p level and as how high. Then, as you were saying, the vacuum polarization and the structure of the particles, it's an issue when you start to calculate, when you want to go into the precision realm, even in QED. Unfortunately, the Kaon mass is taking over on all these errors which are in this context. I don't know, Simone, if you want to make some comments related.
No, that it is important, for example, for the extraction of the Kaon mass. For example, if you just use the non-relativistic formula to evaluate the uncertainty on the mass, depending on the value of the energy, then you don't get that value of the mass. You need the QED correction to extract the value of the mass and uncertainty from the value of the transition energy.
So
He's our expert in
yeah,
this.
yeah. Experimentally, you are using these X-rays to somehow
Yes.
pinpoint all
Yes.
these energy differences and so
Yes.
on. Okay, so in that sense, you have a handle on the K and mass also.
Exactly.
Yeah, yeah, because
We
I
should have.
Yeah.
And that's what we want to do. It's a kind of a circle, because to have the Kaon mass, you need to have the Kaon mass. So it's a kind of a
Self-consistent.
yes, yes. But it's
Interesting system. Actually.
it's absolutely fascinating.
Hadronic atom.
Yeah, hadronic atoms, right?
Are there other hadronic atoms at all? I mean,
Oh yeah, they are the antiprotonic ones,
Mhm.
the sigma minus ones,
Okay.
the pionic ones.
Okay.
The pionic ones reach a level of precision, kind of orders of magnitude better,
Okay.
at
Yeah,
PSI
because
in
Pion
Switzerland.
is very simple.
Yeah, and there are also very intense fluxes of pions, orders of magnitude higher than you can do with kaons, because a lifetime it's 100 times higher,
Okay.
so you can keep them alive longer.
Yes. Okay. I see. Okay. Thanks.
Okay, please.
Compared to the muon capture and tau capture, pions and kaons are mesons, and as already you said with Yoni, are hadrons.
Yeah,
So the treatment I understood is approximately same, because I assume in the muon capture and tau capture that it is captured in the upper atomic levels and it cascades down.
yeah.
Which of the two mesons, pion or kaon, is the mean life is longer?
Pion,
Pion,
definitely
pion.
pion.
Then
I have to say that tau does not form now, lives too short. You don't have time to form tauonic atoms, unfortunately. It's too short.
but it is used in the same way like muon captured by atom. For example, when here in Gran Sasso, they were measuring neutrino CERN, from CERN,
Mhm.
the tau neutrino produces tau particle,
Yeah.
and this is captured. So this was a difficult experiment, Icarus experiment.
Oh,
so-
opera.
And opera. It started as Icarus maybe. Okay. So
Now, Icaro is the experiment of Carlo Rubbia, while opera is the experiment of, and it's a totally different group, yeah.
Okay. But it is Tau particle is also discussed. Tau
Not
physics.
yes.
Not in
Not
your
for
case
us.
because we already discussed previously that the energy is small for E plus E minus collider in your case.
In our case, yeah, it's too small. It doesn't
It's
form
too
neither char nor tau. We are arriving at 1 GeV.
Yeah. So the physics is different.
It's
Although
different and it's complementary.
the assumptions are same.
Depends which. Yeah, it's
And
complementary.
the interaction is different.
The interaction is different, yes. And in a different energy region, yeah. This is threshold. And it's the door from where you enter from scattering to underground world, the under threshold, the bound states. So it's from freedom to the bound states. That's the door, which is at the threshold measurement, which is a very fundamental point.
Carbon capture, I haven't seen any paper. Have you, Yoni, seen?
No, I don't know if it will be captured actually, so it's speed process. But I mean, in principle, yes, if K and
No,
decays.
that's ruled by Strong.
Yeah, but it can be in principle also weak interactions because K can decay to a lower hadron, so lower mass hadron, and then emit something like leptons and so on. I don't know if this is possible.
Could be, but not in our case. That was what the Chloe experiment studied, another experiment.
Okay.
For us, the kaon is infinitely lived because the cascade is 10 to minus 12 seconds. Kaon lives 10 to minus 8. So it's like living forever.
If you mean in also the weak interactions, then it will be Kali already. But in principle, I think it would be. I mean, also weak interactions.
Yeah,
With
we
K
will
and
discuss
and
this after Luca's talk because he will address something.
Okay, please.
Okay, I have curiosity please. So, in these bound atoms, what are the orders, let's say, of the average kaon nucleus distance, like you can define for the electrons in normal atoms?
If I remember well, it's kind of 80 Fermi in the conic hydrogen.
And is this, I can make the calculation on my head, is this consistent with the ratio squared of the electron mass and the kaon mass?
Yeah, it is.
So it's not,
It's calculated based on that.
okay, so it's not hugely affected by QCD effects, this
No,
average?
it's on the tail. So the overlap of the wave functions, it's on the tails.
Okay.
Yeah, it's not a very strong overlap.
Okay, I see.
It's,
So,
yeah, it's on the tails.
okay.
And it's on the tails, but it's important because the strong interaction is short range.
Mhm.
So that's the issue. How long it extends, where the tails gets. And
I
that's
see.
the very interesting issue. It's not strong overlap,
Mhm.
marginal.
I see. Thank you.
Okay, others? If not, I thank again.
Thank
to
you
the-
very much. Thank you.
Before going to the coffee break, I want to make an announcement. Will be an addition